T1 and T2 has a threshold voltage of 1 voltage. The device parameters K1 and K2 of T1 and T2 are 36 microampere per voltage square and 9 microampere per voltage square respectively. The output VO. So here the question is asking us to find out the VO, and they have given the K1 and K2 value, that is mu and COX. Mu n or mu p COX depends on which MOSFET we use, but here you have to figure out which MOSFET it is. Like when you see 3-line MOSFET, like usually if you see MOSFET given like this with 2 lines, you know that if the arrow pointing outward, that's an NMOS, and if it's pointing inside, that's a PMOS. But for this one it's different. For this one, if you see the arrow pointing inward, that's an NMOS, and if the arrow pointing outward, that's the PMOS, when you have 3 lines like this. So you have to know this is an NMOS right now. So for the NMOS, we know that the drain is on the top, and then this is our gate, and then this is our source. Okay, and also this is diode connected with the gate and the drain, so whatever the voltage here should be equal to whatever the voltage here. So VD should be equal to VG, VD should be equal to VG, and there's no resistor or anything, so there's no voltage drop. So what are the voltage here? It should be exact voltage right here, so that's 5 voltage. So this is equal to 5 voltage. Okay, and this voltage at the source, that's equal to the V0, and this voltage at the source is exact voltage we are going to have at the gate for the second one, but let's look at the second one later. Let's deal with all the first MOSFET only, that is first NMOS. So for the first NMOS, VD is equal to VG, which is equal to 5 voltage, and then the VS is equal to the V output, and also the V threshold is given in the question, threshold voltage of 1 voltage, so VT is there, and the VDS, drain source voltage, VDS is nothing but VD minus VS, and we know that VD is 5 voltage and the source voltage is V0, so 5 minus V0 and then VGS, exact same thing, because whatever the VGS is VG minus VS, and VD and VG are 5 voltage, so this one also 5 minus V0. Okay, and this is in which region? If you look at carefully, this VDS absolute value is greater than VGS minus VT. How it is? You can see like VDS and VGS same value, and for VGS if you subtract VT, that's 1 minus 1 right here, so this is going to be 4 minus V0 after you do that, and this is 5 minus V0, that's greater than 4 minus V0, so you can say VDS is greater than VGS minus VT. So from this you know that this is in saturation, because the condition for the saturation is it should be equal or greater than VGS minus VT. This is not equal, but it's greater, satisfying the condition for saturation. So this one is in saturation right now. Okay, and that is one thing, and let's go ahead and continue in the next page. So now I'm going to look at the next MOSFET right here. For the next MOSFET also, like this is an NMOS, you can see the arrow pointing inward, and for this one the VD and the gate is going to be equal because this is diode connected, so we can say VD and VG are equal, and for this one the VD and VG are the V output. Okay, let's name this one as T1. This for the first MOSFET and this for the second MOSFET. Okay, and that is that, and then if you see the source is connected to the ground, so Vs is equal to 0, And then for this one also the V threshold is same for all of them, so this one also the V threshold is 1 voltage. And if we do comparison VDS and VGS minus VT, okay, we look at the absolute value of this. So here VDS is nothing but VD minus VS. VD is V0 minus VS, that is 0, so V0 minus 0, that is V0. And VGS minus VT is VGS is VG minus VS. So VG is V0 minus VS, that is 0, so that is V0, but we subtracting another one, that is VT. So this is V0 and this one is V0 minus 1, so this one definitely greater than VGS minus VT, therefore this is also in saturation. So we can say T1 and T2 are saturation. And therefore we can use the current equation, that is ID is equal to K times VGS minus VTS square. Okay, it should be half. If you look at the train current equation, that's half Kn mu naught. Half Kn is basically mu naught CX, so half Kn times VGS minus VT square, or you can say V over drive square. Both of them are right. So in this case, since we have two different VGS, we can say VGS minus VT square. Okay, this is the train current equation. So we can apply this one and solve for the output voltage. Now let's see how it's gonna happen. So if we equate, and here, okay, so this is we have the Kn value, that is mu a over V square, that's given by K1. So you can also say ID is equal to, according to that, ID is equal to half K times VGS minus V threshold whole square. And now we have to just equate both of the, since the current flow through this one is going to be the exact current through this one as well, because for the MOSFET there's no current flow through the gate, so whatever the current flow through the drain must be equal to the current through the source. So the source is the source of the first MOSFET is the drain for the second one. So for the drain it flows exact same current, and that's gonna go through all of them. So from that we can get the relationship that ID1 should be equal to ID2. Okay, so based on that we can create the equation K1 VGS1 minus VT whole square. I neglecting the half because it's going to cancel both sides half, or you can just put it and cancel also to show the illustration. So half K2 VGS2 minus VT square. The V threshold is same for both of them, so that's why we put VT, but VGS1 and VGS2 are gonna be different or same. Like, let's see what happens. Half cancels, K1 and K2 are different. That is, K1 is given by 36 microampere per voltage square, K2 is given by 9 microampere per voltage square. So 36 and 9, 36 VGS1 minus 1 square, and then this is 9, and then this is VGS2 minus 1 whole square. Okay, and for the first one, VGS is nothing but VG minus VS. So I think we know the VG, that's 5, and VS is V0, so we can substitute that. So 5 minus V0 minus 1 square. And for the second one, VGS is nothing but VG minus VS, and VG is V0, V output actually, and then Vs is 0 minus 1 whole square. Okay, now it's looking better because we only have one unknown variable right now, so it's going to be easy for us to solve. So 36, and this is 5 minus 1 4, so 4 minus v0 whole square, and in the other side we are going to have 9 v0 minus 1 whole square. Okay. So if you square root both sides, since this is 36 and 9, it makes that one even simpler. If you square root 36, that's 6, and then if you square root 4 minus v0 square, that's going to be 4 minus v0, and then if you square root 9, that's going to be 3, and then if you square root v0 minus 1 square, that's going to be v0 minus 1. Okay, now we can expand this one. So 6 times 4, yeah, I should have done one thing as well, like yeah, you can divide this one and square root. That one also made it simpler, like 36 divided by 9, that is just 4, so you will just get 2, and that way also okay, but it should be giving the same answer. So 6 times 4, I can do right now, make it simpler. 6 divided by 3, that's 2, so 2 times 4 minus v0, and then v0 minus 1, and then 2 times 4 is 8 minus 2 v0 is equal to v0 minus 1. Therefore 3 v0 is equal to 9. Therefore v0 is equal to 3 voltage, and that's the output voltage. That's what the question is asking for. Okay, and that's it for this video. I hope you guys found this video helpful. Thanks for watching. Don't forget to subscribe.